Thank you very much for joining me for this third part of our roadshow presentation, The Rise of Mechatronics. In this presentation, we're not going to show what's exactly going on as we speak, but rather what we're trying to do is to facilitate some thought as to where mechatronics design can go. Because at this point in time, we can talk about how we can do collaboration of tools, and that's what you'd call the first and second generation of mechatronics software. However, the third generation of mechatronics software is really going to require us to do simultaneous electrical and mechanical drawing. We have to have the right manufacturing tools in order to facilitate this type of design. So let's take a look at a couple of things here. What's interesting about this slide over here is that if you look on the left side, you're going to see what I'd consider to be some of the major feats of mechanical engineering. We can take a proton or an atom and we can smash it. We can take equipment that's built here on Earth and put it into the sky. We can also put it on the moon. We've put it into orbits of other planets. We've even sent things onto Mars as well. When it comes to our design of buildings, our skyscrapers, especially in the newer cities like Dubai and in Shanghai, they practically defy gravity. And lastly, if you look at our transportation, it's really amazing what we have done since the last 100 years, especially with the automobile. We can now get across the United States in 5 to 6 hours with an airplane. Well, if you don't have an airplane ticket, you can drive it in 3 to 5 days. Now, if you had asked me to go from one side of the country to the other side of the country, and this was 150 years ago, I would really be risking life and limb to make that journey. On the right side here, we have what I'll call some of the feats of electrical engineering. On the very top there, you see an example of an MRI. And the neat part of an MRI is that it's non-invasive, meaning we don't have to cut the body open in order to see inside of it. If we look at all the devices right next to it, look at all the things that we use in order to look at things or to see things or to hear things. And what's also amazing about that picture there is that really with the exception of the headphones, all of those things that you see I can do on my smartphone. So in a sense, we've not only had a revolution in electronics, we've also had another revolution in which all of those things that we have done can be done in something that fits in our pocket. If we look at the bottom picture, we also have power. So most of us aren't necessarily walking around our houses with candles unless you've been involved in a major storm or you're just really trying to save $1 or $2 on your power. But really, if you think about it, candles have now been reserved to either emergency use or for decor use. They are not the primary source of light when the evening comes. And lastly, we just look at our computing power. If we need to figure out what the tangent of something is, or we need to figure out what the square root of 37 is, it's really just a matter of us typing it in and getting the answer instantaneously. But long ago, that was not an easy answer to obtain, and we would have had to gone to books that have tables of this information in it. And how did those tables come about? Well, somebody actually sat down, probably by candlelight, and actually derived those numbers by trial and error. Now we don't have to worry about that. It's really just the press of a button. So there's some really great accomplishments both on the mechanical side and on the electrical side. But the big question is, where's Rosie? Because when you really look at what we've accomplished, they've either been mechanically centric with electrical assistance, or they have been electrically centric with mechanical assistance. But in order for us to get AI, or in order for us to really get what I'll call mechatronics design, we're going to have a 50-50 blending of both mechanical and electrical. First and foremost, how do we electrically connect anyway? Well, we can do it one of three ways. We can do it through radio frequency. We can do it through cables and harnesses, and I would include in this fiber optics as well. And then secondly, I would also say that there are printed circuit boards, because in the end, what do we put in our printed circuit boards besides components? We also put connectivity. So understanding this here very simply, let's take a look at a couple of examples. So here's a robotic arm, and as a matter of fact, this robotic arm was made with a 3D printer. And when you look at it, what you can probably tell from it is that first they printed out the arm, and then they put an actuator in there and bolted it in, and then they added in the harnessing afterwards. What mechatronics manufacturing is calling out for, is there a way for us to make each one of those parts of the arm so that the electronics is already in it? So as we are snapping together or bolting together this part, the electronics are already there. So we don't have to worry about the harnessing. It's just a matter that, hey, we put this together and now it's electrically active just as much as it can be mechanically active. Here's another example we'll give you. So this is the Myomo project. a very cool project. It is a real product out there, and it helps a lot of people with neurological disorders. And we see in this example that there is a printed circuit board. So obviously there was a mechanical side and there was an electrical side. And more importantly, probably what this product is doing for that printed circuit board is protecting it. So again, mechatronics manufacturing is asking one of two things. Is there a way for that printed circuit board to actually be a part of the structure? Meaning that instead of trying to protect it, could it have been some way, some shape or form added in so that it actually provided some strength or assistance in the mechanical structure? And then lastly, and maybe we're just looking a little too far ahead, but it's the question we have to ask, is did we even need to have a printed circuit board to begin with? Could the circuitry of this be placed in the plastic itself rather than having to have a separate printed circuit board? So again, these are the things that mechatronics is asking. What's interesting about the electrical folks is that we're very 2D in nature. The progress that we have made in design has really been in the 3D space. For example, if you look at something like AutoCAD, which used to be really the king of mechanical design, well, how did they get kind of thrown off their throne? They got thrown off because SOLIDWORKS came in and said, look, you can design this in 3D. And let's face it, when we're working in 3D, we're working in a real space that we understand because we live in a 3D world. Look at Altium in 2008. In 2008, Altium realized that in order for them to have any type of bridge between the chasm of the MCAD world and the ECAD world, in order to even bridge that chasm, they're the ones who come up with this 3D rendering within the 2D. So in logical progression, we've already gone 3D in the mechanical. We're already using 3D in order to bridge electrical and mechanical. Doesn't it make sense that maybe we ought to be designing electrical in 3D as well? And that's what we're calling out over here. Because right now we draw in 2D, we fabricate in 2D, and I'll talk a little bit about that in a moment. And if you think about it, one of the biggest problems we have with printed circuit boards is that our z-axis is limited in terms of vias. We don't normally think in the z-axis when we're designing boards like the one that you see here in this particular picture. Now, it's kind of important for us to take a step back, and I don't want to go too deep into this. If you're really interested in it, take a look at our PCB fundamentals class because we go into a lot more detail about it. It's something that everybody who's designing printed circuit boards ought to know because it's the current process that we use in order to create a printed circuit board. So the current method is basically you take what is called a core material, and if you take a look at my cursor here in the top right corner, what the core material is basically a dielectric with copper on the top and on the bottom. And what we do in this process is we chemically etch it out. That's how we do it. We basically do a lithography type process and we etch out those areas that we don't want, and what's remaining is our circuit. So it's a very chemical process. Secondly, we build inside and out. So if we were going to do a 4-layer board, we would actually start with layer 2 and 3, and then we would add in layer 1 and layer 4. And lastly, again, we're limited to vias in the z direction. So if I want communication to exist between layers 1 and 2 and 3 and 4, I got to have some type of via in order to do that. So the bigger question is, can this whole concept be avoided? Let's talk about some of the limitations that we're coming against when it comes to fabricating printed circuit boards. So by the way, if you're not familiar with it, in manufacturing of printed circuit boards, we have the fabrication process and we have the assembly process as well. The fabrication process is the making of the board. If you think about it, what we're doing is we're actually building a custom component. And then afterwards, we're populating that custom component with all of the components that we want on there. So that's the assembly process. One of the biggest problems that we have in the electrical side is this control of the z-axis. And why is that? Well, here's one of the issues that we come across right now. One of them happens to do with what we'll call the registration issues. Since we are building inside and out, we can have these situations where not all of the layers line up. So you can see a really great example of this here on the bottom right hand side of the screen. Even though the centers are matched up, if there's a little bit of a registration issue or what they call a delta issue, as the board goes out, we may not be lining things up from one another, and that can cause yield issues, yield losses. That's why if you try to build something that's really small, for example, they may charge you a lot of money for it because you may ask for 10 boards, but they may have to actually make 50, 60 boards to get the yields necessary because there might be some registration issues as they're doing this. Now, on boards that only have 2 or 4 or even 6 layers, not a big issue. But as we mentioned earlier on, when you're dealing with something that's got an FPGA on it and it's got hundreds of pins on it that you've got to fan out, and you've got a large board, you're going to have registration issues because now you've got dozens of layers, and now you've got a board that's probably a couple of inches long and a couple inches wide, and those registration effects are really going to become profound as you go out. So what this is really going to impact are the vias. And if you take a look down here at the bottom right, you're going to see what is really an ideal via. Now, ideal in the sense that we probably wouldn't do this type of thing because there are other ways of distributing a signal. But what you see over here is really a perfect hole with perfect annular rings connected to perfect traces. Well, remember, this is an etching process, and etching processes are not exactly, certainly won't be smooth, but nevertheless, this is what they would consider to be ideal. We have to also remember that, again, now we have registration issues, so maybe these annular rings, which are really nothing more than targets, are the things that we're trying to line up and hit. So these may already be off a little bit just because of registration issues that we talked about in the last slide. Now what we're going to do is we're going to actually take a drill and we're going to send a drill through here. Now in the perfect world, these rings are not only lined up, the drill is going to hit dead center, and it's going to go all the way down, and it's going to end dead center. But if you've ever done this, for example, with a self-tapping screw on a really shiny piece of metal, maybe you wanted to put it in a certain location, but if it didn't grab, it may have slid a little bit and then started to drill in. And so we may not get it necessarily in the middle, but if you look at the middle example of this bad via, and it depends on the class, by the way, of the vias, but you may not even start in the middle to begin with. And more importantly, again, because the drill may not be going straight down, it may actually be going off at an angle. So what you see in the third picture there of what they call the bad via, it may not even be within the target. It may actually punch through the annular ring over here. So in short, we could have a slip and not hit the center. We could be drilling at an angle. We could have both of the above, and then we can have registration issues. So you can see that we have a lot of difficulty dealing with the z-axis. We're very limited with our ability to work in the z-axis when it comes to electrical design. So in addition to the manufacturing issues of it, we also have to understand that there are things called layer pairs. And if people are not knowledgeable about this, they can create and route a board that the software tools will certainly allow, but manufacturing won't be very happy with it, or it may not even be manufacturable. For example, at the bottom right corner, look at what I've got there for layers 1, 2, 3, and 4. Now imagine for a moment that an engineer or a designer who's new to the process decides that they're going to route this, and they're going to say, well, I'm going to put routes wherever I need to. I'm going to have a route between 1 and 2, I'm going to have a route between 2 and 3, and I'm going to be allowed to do a route between 3 and 4. And they're not just using through-hole vias, they're using whatever the start and stop layers that they can set up, and those are called drill layer pairs. Well, they send it off to the folks who are going to fabricate this, and they look at it and say, well, I can do a via between 2 and 3. Once I've fabricated layers 2 and 3, I can stop the process, I can drill the hole, and I can plate it. So that's not a problem. But now you're asking me to also have a via between 3 and 4, and that's very problematic. And yes, I could do it through something called a microvia, which is a relatively new type of via, but microvias weren't not intended to do that type of work. So you know what? I can do a microvia, or you can go back and reroute this and it will cost you a lot less money. The big question is, and the reason we bring this up is that can 3D printing make all of this nonsense that we have to go through with the vias a moot point? One of the things that's interesting about 3D printing is that, number one, it's primarily additive. There are subtractive printers. And what's also interesting about it is that if you go on to the internet and you look at 3D design, you're going to see thousands of pictures out there. But one of the things that we at 9.Connects believes is that some of the printer companies that will arise out of all the companies that are out there and experimenting and selling their product are going to be the ones that can actually dispense both conductive and non-conductive ink. Because what's interesting is that right now, okay, this is October of 2017, if you were to search out 3D designs that have both electrical and non-electrical inks in them, you're not going to find a lot out there. If you look at the few examples we could find, is that number one, people are doing this stuff, and number two, it's going to really force us to rethink the way we create electrical products. If we look at this example up here, it may look a little crude, but this is going to change the way we manufacture. Why is that? Because as I mentioned earlier on, we are fabricating boards and then we assemble. So what we're doing is we're creating these boards and then we take our components, we put something called solder paste on them, stick them onto our boards during the assembly process, and then we send them through a reflow oven so that they will become permanently bonded. What you see up here is very different. What we're doing here is we're starting with a non-conductive ink, we're stopping the process, we're putting the component in, and then we're building the circuitry around the component. That's very different from what we do right now. That allows us to do some interesting things. Like if you look at these examples over here, we may actually even be able to do things in a 3D space where we just stop our process after we've done so much non-conductive ink. We stop the process, we put in our chips, and then we continue along by putting in the conductive ink and trade off between the conductive and non-conductive inks. And it looks like they've already, or some people have already been successful in doing these type of things. The big thing that this is really going to buy us is better control of the Z-axis. One thing I like about this one product that they did down here is that you can see that the traces are the same no matter which direction you're going in. Because one of the things that we have an issue with, and I'm going to jump back over here a little bit, back to this picture here, is that in high-speed design, vias are a bit of a bane. And the reason that they're a bane is because one of the rules of thumb when you are doing high-speed design is that you always want to keep the width of your trace the same. And the minute you change it, you've changed the impedance. So follow along with me. Now, for those people who are familiar with high-speed design, we'd have something here that's called a stub, and we don't want stubs because they act as accidental antennas. But what we want to do is, let's just take for a moment that we have this trace coming in here and we have the signal going out over here. Forget about the rest of it, the top or the bottom. The fact of the matter is that if we have a trace coming in, we have a certain width, which gives us a certain impedance. It hits this round thing called the annular ring, and now we've got a different impedance. Now we hits this cylinder here, right? This is our barrel that's going to go down, and it's now got another impedance. It hits the next annular ring, it's got yet another impedance, and then it goes back into the trace, which has yet another impedance. So we have 4 impedances that are going on here, and that's not good for high-speed design. And one of the things that we think is going to happen here is that with 3D design, we don't have to worry about vias anymore. This primitive that we've been so reliant on for the Z-axis would actually go away. And that a trace is a trace regardless of the angle or direction it's being placed in the 3D space. And of course, the second thing that'll be really great about this is that we no longer have to put components on the top or just the bottom. We've got a cube, and a cube is 6-sided, or even if it's a cylinder, right? And if maybe the concept is going to be a cylinder shape, and I can see merits to this, you know, now you have the whole side to work with over there, and at any angle, not just the 4 sides of it. So some neat things that are coming out. Obviously, people have been successful with it because we're starting to see some prototypes of it. But this is something to consider in the next couple of years as this whole printer industry is rising and people are vying and jockeying for position within this budding industry. So what's the takeaway from all of this? There's a couple of things that you can think about. First and foremost, if you are an electrical engineer, look at SOLIDWORKS CAD. And if you are a mechanical engineer, look at SOLIDWORKS PCB. Look, in short, look at the other person's tools. What are they doing in it? Because you'd be really surprised at how different they are. And I'll give you a really great example. When I took the class a couple of months ago for SOLIDWORKS CAD, the one thing that became very obvious to me is that there's no grid. Now, that's very different coming from the electrical side where everything's on a grid. And when I used to do Altium support, a lot of questions that came in or a lot of the problems that we had to solve had to do with not being on the grid. Now all of a sudden we go into the mechanical tool, we're not dealing with grids anymore. We're dealing with relations, a very, very different way of looking at how these lines and these extrusions work together with each other. So there's a really great example there of how we have to start thinking in a very different way. The second part is collaborate on libraries. Now, during the roadshow, we asked everybody at the end saying, okay, who's got a really cool library that they would be happy to present? And on the electrical side, nobody raised their hands. Everybody has problems with their libraries, especially on the electrical side of things. And one thing I have found is that the mechanical folks tend to have a better grasp and they do a better job with maintaining their components. And so one of the things that's going to happen in mechatronics design is there's going to have to be a collaboration on libraries because you want to pull from one unified library. The electrical folks shouldn't be pulling from one thing and then telling the mechanical folks to do something, and vice versa. The mechanical folks shouldn't be doing something and telling the electrical folks to develop it. It has to be one unified library. Spend some time in 3D printing, and you'll see that in 3D printing, there's a lot of cool things that you can do with it. But the reason I'd recommend that is, again, in electrical design, we design inside and out, where in 3D printing, we are going to do an additive process of building from the ground up. And we have to have that insight in order to understand how we're going to put our circuit together. Because I can think of a lot of cool 3D mechatronic type of designs that have electronics in it. Half the battle is understanding how can we do this? What are going to be the steps necessary for us to do this both electrically and mechanically? If you're not familiar with it, take a little brush up on circuit theory, because that's always a good thing to understand. You don't have to get super deep into it, but just understanding where you have your complete circuit and your loops and your grounds and those type of things. One of the things that we've done here at Nhuan.Connects is we developed an in-house project called a rangefinder. So one of the things we're going to do now that we've developed this is that we will be putting out a blog in the near future. And with this blog, we're going to try to break down all the elements of the electrical side. What did it take to come up with the libraries? What did it take to do the schematics? What did it take to get it into a layout? What did it take to get it into manufacturing? So we want to break that down so that you can see the entire process. And yes, by the way, we have built the rangefinder. In fact, we've built 2 generations of it, and we're already looking at the 3rd generation. And again, the whole purpose of it was really for show and tell. If you're looking for PCB design practices and process, take a look at our website under our knowledge category. We designed our website so that it could really be a beacon of light in a world that has PCB information scattered all about it. And lastly, what I want to talk about is a course that we offer here at Nhuan.Connects called PCB Fundamentals. And we put this together because we realized that there really is no source out there to introduce and teach someone the entire PCB process. You can find a lot of great articles out there. You can even take a EDA type of tool class that can show you at least the schematic and the layout side of things. But we have not found anything out there for the individual coming into printed circuit boards, or those who are somewhat familiar with printed circuit boards but don't have the whole story. So what is the purpose of this? We're not trying to teach design. What we're trying to teach is the process. And we've designed it so that anybody can really be involved in this. And it's not just for the designers or for the engineers, though they would probably be the ones who make most use of this. It was also written for technicians. It was written for program managers. It was even written for the purchasing folks who have a role in this as well. So if you understand what the PCB process is, then you understand what the needs of manufacturing are, and you can design accordingly. Because one of the things we forget when we design printed circuit boards is we're not designing circuits, we're designing for manufacturing. And when we don't design for manufacturing and we forget those little things that really are easy to forget when we're looking at a computer screen, they really cause a nightmare down the road when we're trying to get this through the fabrication and assembly process. The other reason I make this known to you, and you're saying, why is he talking about PCB when this is a mechatronics thing? In order for me to even have an intelligent conversation about how mechatronics design is going to look, I got to understand the PCB manufacturing process. And if I understand the differences between the two, then I can have an intelligent conversation about, okay, this is the conventional process and this is where mechatronics must be going in order for it to become a 3D design. I hope you enjoyed this series of presentations that we gave. If you came to our roadshow, thank you very much. If you missed it, well, hopefully this makes up for it. And we look forward to having you at our webinars in the future. Thanks for your time, and you take care.